No. Okay. So today there we go. Going to cover section 2.3 or most of it. This one is a model with a single stock. If we remember the bathtub problem, it has a single stock because there's water going in and water going out. Water is the stock. It's the only one. Whereas if you think about the great Pacific garbage patch with all that items in there, that was a lot of different stock. You had plastic bags, you had nets, you had bulbers. I mean, it was just a lot of different stock, where this section is just talking about one stock. And in this case, it's water. If we open a faucet to fill a tub, water will flow, and we talked about this earlier, at a constant rate. If we open the drain as well, water will flow out. But we were looking at it as a constant rate before, but technically it's not a constant rate, because when you think about the water in the tub, if it's full, it's going to go faster. And then as it goes down, there's less force pushing the water out. So then it actually goes slower. So the amount of water in the tub makes a difference on how it's flowing. On page 96, there's a picture of it. Here. When they're doing these pictures, this little gray area out here, it's just your water. It doesn't have a lot of significance, and that's why they put it in the gray matter. But the blue arrows are which way the water is flowing. And then the red is where water could be changing. The red arrow denotes a control. So it's not necessarily at the same speed. Whereas the faucet, yes, we control the flow, but once we stop turning it, then the control stays constant. Where this changes by the level of the bathtub. And that's why this is a change. Any questions so far? So they're showing that on this here. Instead of algebra, we can do it by graphing, but I'm going to show you the algebra first on finding this line. I think for this course, you should be able to do it with graphing. No, they told us that the inflow was constant, 2.2 gallons per minute. Somewhere. Oh, it's probably in the book, and I just didn't write that part down. Well, let me move it. But it's in the problem. They told us this was the flow. And then the outflow, when it's 2 inches in the bathtub, it's flowing at a rate of 0.92 gallons a minute. And when there's 1 inch left in the bathtub, it's 0.46 gallons per minute. So we could find an equation from this. We would first find our slope. from this. What that means is this is your X and this is your Y. And you just subtract them. So 0.46 minus 0.92, 1 minus 2. We could have went the other way so that we had both positive. So if you use this first, you have to use this first. If we started with 0.92 here, then we'd have to start with 2. Any questions on that?
Does it matter if you do it the way that makes it negative or the way that makes it positive?
No, and that's why I wanted to show you is you could do it either way. Just make sure whatever, like notice that this point goes together. So whichever one of these you choose first, you have to choose the same one on the bottom.
Okay, thank you.
Mhm. Now, we also know that if there's no water in the tub, there's no flow in the tub. So at time 0, it's 0. So there's nothing added on here. Any questions on finding the slope? If we go on Desmos and graph it, we know we have this constant. And the constant is a horizontal line. Now this one, I'll show you 2 ways. If we didn't find this equation, we could still find it with those 2 points. Now it's going to be a little bit different because I also use the 0, 0. To just plug in points, you go over here to this plus sign and go to table. And then you put your X's, 2, 1. We could put the 0 in too and see what happens. I didn't try it with the 0, but. And then let's see, 0.92. 0.46 and 0. Any questions so far? So for the horizontal line, that's not letting me go up there. Oh, here it is, 2.2. To get a table, so if you have points and you want to draw the equation, because we want to see where this is going to hit the red. That's where the equilibrium is. You hit this plus sign and you go down to table. And that's how I got these. And then I just typed in the the points that I had, this one, and I knew when the tub was at 0, then there was no water coming out of it. To find the equation, notice this is x1 and y1. An equation is y equals mx plus b. Oops. Yep. But this is x1 and y1, so we want y1 and we want x1. Also, in order to find the equation, instead of an equal sign, we use this symbol. This symbol, if you go on your keyboard and look at the 1, it is right next to the number 1, to the left of it. So we're going to type that. We're going to type y. Now you don't have to get it to go down. If you hit 1, it automatically goes down. So y1, and then to the left of your number 1, you have to hit shift and that key. mx1. And we don't really need b. Will it put something if we put b? Yeah. Notice that for b, 10 to the negative 18, that's 0. And 0.46, that's what we got here. So this was one way of finding it, using an equation, or we can use a graphing utility. Any questions on that part? Move this over a little. Is everyone getting the graphs? I want to find as many ways of using the technology rather than having to have strong algebra skills, because I know this isn't a class like that you want to learn a lot of math. So I'd rather have you learn more material and understanding sustainability and how to understand that with more technology. So as much as possible, if we can use, and I like Desmos because it's free. Just click. Now we want to find the point where the 2 lines cross, because that would give us the depth at an equilibrium. And we should get about 4.8 inches. So if we look at Desmos again, notice where the 2 intersect. Another thing that's nice about Desmos is if you click on it, it gives you it. Click on it twice and it'll stay there. 4.8. So when the bathtub is 4.8 inches, then it will be in an equilibrium. Any questions on that? Note that in this problem, we measure the stock of water by looking at its depth in the bathtub rather than its volume. So we're only talking about how many inches it is. We're not talking about how much water's in the bathtub. We can do this because the volume of water in the tub is equal to the depth multiplied by a constant. So if we want to find the volume of the water, it's the depth, how deep it is, multiplied by a constant. They're saying that, and I think some of the material in this section, they're making it too complicated. I don't think a mathematician wrote it. It says the cross-sectional area of the tub. They're just talking about if you have the bathtub length and width. And then we multiply that by height, because volume is length times width times height. Now they're saying that this volume is constant. Now, depending on the bathtub, some bathtubs bend outward. That wouldn't necessarily be the case. They're assuming pretty much a square rectangular bathtub, straight. So that length times width saves the same all the way up. Then you would just have to multiply by your height. So they're saying that length times width, or the cross-sectional area of a bathtub, is 8 feet squared. So maybe it's 2 by 4. So then this area is 8 feet squared. Then if you multiply by your height, that tells you how much volume you have or how much water's in there. Any questions on that? The water in the tub at equilibrium is a box of base area 8 feet squared and the depth 4.8 inches. Now, if we want to find the volume, though, these two are not in the same units. So we need to change this to feet, because volume is usually cubic feet. Well, not always. That's what they're asking for. But you don't want to go to inches, because then if we want to go to gallons, we got to go to inches to feet to gallons. And so we want to go with feet. So you need to convert 4.8 inches to feet. How would we convert? And you can use proportions, or if you just know 1 foot is 12 inches, are we going to multiply or divide by that 12? Anyone? So the in-class exam is next Friday. By in-class, I mean on Zoom. You'll have your cameras on. Make sure it shows your name. So if you're using somebody else's computer, change the name when you get on. But it will be simple. Don't let all of this get you bogged down. I want to make sure you're able to convert things, and we will review next week everything that you'll see. But the big thing is that you're able to convert units, and even just when I went to buy carpet for the first time when I got a house, it was just so confusing because I measured it I think I measured it in yards and they were in feet squared. And I'm like, wait a minute. And I had to think about how to do that. And so it's things you should be comfortable with. And that's what your test will be about, the basics. Converting this to feet, absolutely, you need to be able to do that. Now, if you weren't sure whether to multiply or divide, because we know 1 foot is 12 inches. I know you know that. But then I have to decide whether I put feet on top or bottom. Well, this inches is on top. I want it to cancel, so it needs to be on the bottom. When you're canceling units, one has to be on the top and one on the bottom. So even though it's making my value really small, I need to divide by that 12. Any questions on that? So it's 4/10 of a foot. That's the height of the water in the bathtub. Now, if we want to find the volume or the amount of water in the bathtub, we know this is our height. We multiply by the area, which we said was 8 feet squared. So it's 3.2 cubic feet. Any questions on that? I cannot visualize 3.2 cubic feet. I could visualize gallons if I knew the gallons, because I can think of a gallon jug of water. But 3.2 cubic feet sounds small. It's actually not. Because 1 cubic foot, I forget now, 1 cubic foot, 7.5 gallons, one. So if we go to convert this to gallons, 1 cubic foot is 7.5 gallons. So take these cubic feet and change it to gallons. If we go, start with your 3.2. And convert it to gallons. Are we putting gallons on top or bottom? Anyone? You could type it in the chat.
On top.
We're putting gallons on top. That way, when we put the cubic feet in the bottom, they cancel. Then we have what's 24? Yeah. So it's at an equilibrium. The amount coming in and the amount going out is at an equilibrium when we have 24 gallons. Any questions on that? Any questions? Okay. Let's try another one. A certain lake contains 10 million cubic meters of water. Water flows into the lake at a rate of 30 cubic meters per day. 10,000 cubic meters per day leave in evaporation, and 20 cubic meters per day leave with an outgoing river. A factory on the lake begins to dump 0.3 tons per day of a highly soluble and well-mixed pollutant into the water. Find the equilibrium amount of pollutant in the lake in tones, assuming that the pollutant does not co-distill. That is, it does not leave the water along with the evaporating water. And so we do have water that's evaporating, but we're assuming that this only leaves with the river, not with the evaporation. Water along with the evaporating. A pollution problem like this involves two materials, a pollutant and a substrate. That's the lake water in which it's mixed. So you have your pollutant that's going into the water, it's mixing with the water, and that's what they're calling the substrate, is the water. In calculations, a key role is often played by the concentration of the pollutant. When you're finding concentration, it's the quantity of the pollutant divided by the quantity of the substrate. So it's the amount that's coming in, the pollution, and then how much water is in the lake. Since the two quantities have the same units, the concentration is a pure number. Remember, that makes it a percent of the pollutant in any sample of lake water is the same as that of the whole lake. So if you took a sample, what's in one spot is all over. In particular, the concentration of pollutant in the outgoing water is equal to the concentration in the whole lake. The solution below depends on, well, this idea, but we're going to solve it. Compute the, I thought I had a part two. Yeah. We're going to solve first, and then we'll do this part. Piece of paper. All right, we're going to let P be the total tonnage of pollutant in the lake. And then the concentration of the pollutant in the lake water is so we have the quantity of the pollutant, we're letting that be a P. The quantity of the water is 10 to the 7 tones. They told us how large the lake was. I didn't want to have the answers in there, so I'm not showing the answers, but they did tell us the amount in the lake. 10 million. So a certain lake contains 10 million cubic meters of water. And then these are the outflows. But the chemical, this is the inflow. The chemical, this is evaporation, so it's not being affected by this one, but it is by this one. So this value was given. This is the amount of water in the lake. Since the mass of 1 cubic meter of water is 1 ton, the amount of pollutant leaving with the outgoing flow is so if we start with this, we want to convert this to how much per day. The amount leaving is this one. We're not using the other one because that's evaporation and the chemical isn't leaving there. And how they're getting, so it'd be 1, 2, 3, 4 times 10 to the 4th. And their cubic meters is the same as a ton. So the 20,000, it can be written as metrics, or we could have put 20,000 here. Each day. Any questions so far? Now, we could divide these, but we would have, they're getting, let me show you how we're getting. So the pollutant that's going in there takes 500 days to leave. Now, the reason they kept this way, if we would divide these, when you're dividing, it's the top minus the bottom. So this would be 4 minus 7 and -3. And this is our pollutant. Now this is a 0.002. This is a small number, but we don't know what our pollutant is. So writing it this way, it's harder to understand what's happening here. We can see the pollutant in tons. Well, tons cancel, but the pollutant takes 500 days to leave because that's your concentration. So the pollutant takes 500 days. If it stopped coming in, it would take 500 days to be gone from the lake. Now to get that, instead they took 0.002. This is the same as this. Because remember, we can make this a fraction. 1, 2, 3. 2 over 1,000. And then divide top and bottom by 2. We have 1 over 500. So it was just another way of writing it. Because this was a little awkward and small, and we don't know what P is to multiply it times it, we don't need the T there. Because a T can cancel. But we don't know what the pollutant is. So then they rewrote it as a fraction to make it easier. One pollutant takes 500 days. So when they dump one time into the lake, it takes 500 days, almost 2 years. And if they keep doing that, then that's going to take even longer to get it cleared out. But if they stop, then it would take approximately 500 days. Any questions on that? Okay. Compute the residence time of the pollutant in the polluted lake. Now, remember, we have a formula for this. It's level of stock. Oh, wait. We found this one already. Oh, I missed one. We're gonna use that formula. But they wanted this, they wanted us to find the P. We knew this. I didn't read the whole first question. They wanted us to find P. So we know that it leaves the lake in 500 days. But we also know it's going at a rate of 0.3 tons per day. Because they told us that. So from knowing how much is being dumped each day, we can find out what P is. Because I know it takes 500 days. And how much there is total divided by the number of days is how much per day. And we can multiply by 500. So then the days will cancel also. So we can multiply the 500 to the other side because we're dividing it. 0.3 times 500 is 150 tons. So the pollutant is 150 tons. That's when we're at our equilibrium. Any questions on that? So this was the pollutant divided by the total water. And then we wanted to convert it to find out how much per day or how many days. In this case, we couldn't go per day because it was too small. So we decided to go per 5 days, 500 days. Then to find out how much P is in the water when it's at an equilibrium, we know that this much is going out per day. So we set it equal to that. Multiply both sides by the 500 so that we get P by itself. So 150 tons of the pollutant is in the water when it's at an equilibrium. An equilibrium means the same amount coming in as going out. Any questions on that? The last part is just asking for the flow rate. But we found it here, 500 days. compute the residence time. That was level of stock divided by the flow rate. And you'll get the same thing. It's just showing you two different ways of finding it. If we took the level of the stock, we said we just found was 500, or no, it wasn't, it was 150. And it's leaving at 0.3. And 150 divided by 0.3, I believe is 500. So it's another way of finding the same thing. Before, we didn't know how much pollutant there was, but we were able to find out the number of days. Now that we know how much pollutant there is and how much is going out per day, we can find the number of days. So it all depends on what information you're given, what order you find things. But any questions on that? The reason these are important is because if we know on average how long a pollutant's going to be in a lake, then we can set realistic timetables for cleanup efforts. Even if the pollution source is shut down tomorrow, it's still going to take a year or two, because it said 500 days to get everything out of the lake until it returns to normal. So when you're telling people that they can't use the water for so long, it's because they've done tests and know how much is going out and how fast it's going. And then they can figure out, as long as nothing else is going into it, how long it will take. I live near a park, and there was a huge rain flood, and the bathroom drains went into our lake. And so then at our park, fishing, boating, everything for an entire year, you weren't allowed to do anything because the lake had to clear out. And so that's a place where you would use something like this. Any questions on it? I know it seems a little complicated. Don't get nervous with the complication part. I just want you to understand the processes they go through. But any questions on it? Did anyone see the explosion? The train explosion? That wasn't far from me. Maybe an hour. But in that area, because of the chemicals that were on that train, they took a whole square mile and evacuated it. Those people are not allowed back there. We don't know how long it's going to take. They're going to run tests like we did just here, looked at, to see when they can come back. So a lot of them had to leave, go to shelters. So it's definitely things that happen. It's not always water. But any questions on that? I don't think I made another problem. I did. Any questions? How about on the project? Is there any questions on the project? That's due this weekend, I think. Yeah, so it's due February 12th, this Sunday. Actually, remember the main post is due on Friday. And then you respond to at least 3 students by Sunday. And any questions on it? Only a couple people have done it so far. Any questions? There's a sample one right here, and then the steps for the project. And this one tells you what your disaster is. Any questions? So quiet today. Okay, if you do not have any questions, I will see you tomorrow. If you do have questions, stay on and ask.